Okay, well, welcome to Grand Rounds on the last day of spring before winter starts again. We're delighted to see everybody here and welcome everybody online. We have a very special guest today who has flown in from Sweden to be here today for Grand Rounds. And introducing our guest speaker is our own Dr. Carrie Gleason from Geriatrics.
Thanks, Lynn. As thank you. So yeah, as Lynn mentioned, Dr. Karikari is coming to us from Sweden today, where he maintained an academic appointment with the University of Gothenburg, but his primary appointment is with the University of Pittsburgh, where he's an assistant professor of psychiatry. Listen to this. He's the director of the Biofluids Biomarker Laboratory, director of the Mass Spec program, the director of the Single Molecule Analytics program, and he is the co-director of the Neurogenetics and Biomarker Core of the University of Pittsburgh Alzheimer's Disease Research Center. Is anyone else wondering how an assistant professor is in a role of director? And the answer is simple. He's an incredibly talented and accomplished assistant professor and has shown his leadership skills. So he's clearly, it's evident that he is an emerging star with multi-talents. So Dr. Karikari obtained his degree in biochemistry and pharmaceutical biotech before obtaining a PhD in clinical chemistry. And then he did postdocs in neurology and neurochemistry at Harvard and the University of Gothenburg, respectively. So but it didn't take long before he began to make his mark on the field of biomarkers and especially blood-based biomarkers. So he was instrumental in developing and refining a novel biomarker p-tau 181 assay. And he also has developed one of the only, this is incredibly novel, a brain-derived tau. And this will be incredibly impactful as we move forward in the field. So just a singular influence on the work in blood-based biomarkers. But important, I think, on another level is Dr. Karikari and I originally connected over his shared interest in inclusive research. So it's not just enough to bring this technology and this science forward to the field. He has an ethos of making sure that we are inclusive in our research. So incredibly admirable. So he's one of the most sought after speakers. I counted almost a dozen talks in less than 2 years, international talks. So I'd love to see your frequent flyer miles account. So. I will turn things over so that you can see why he's such a sought after speaker. And if you have a chance to talk to him, see what he's just a stand-up guy and an outstanding scientist. So welcome, Dr. Karikari.
I'd say don't believe anything she said. So. Yeah, it's a true honor to be here. It's my second time being here in person. And I might say that the very first time I ever gave a keynote was at Wisconsin. And it was virtual, actually. So the photo that was taken, I said that photo is going to be the photo in wherever office I get to occupy. But yeah, so whatever, wherever that we're going, whatever we are contributing, I do appreciate the visibility that you have given and that you appreciated that because, age and several other things are not on our side and that a lot of times you would get to be overlooked. So yeah, it was difficult to find something to talk about today because we have talked about a lot. Like it's been everyday blood biomarkers, and actually sometimes gets quite boring, at least to us in the field. So I thought with the changes the field is seeing with new drug approvals coming in, probably we should talk about that and how blood biomarkers could fit into. And that's what I position my talk today to be on. Yeah, and these are, ICP aspects. So yeah, so as blood markers in the days of approved therapies, that, we've talked a lot about how the blood markers are useful with focused on diagnosis, we focused on clinical trials, and we're waiting that eventually there will be good therapies. But now there are therapies being approved and coming in. So it means that we have to actually think about how we use these ones. I do not have any relevant financial disclosures. So I'm going to do it in quite an unusual fashion. The first aspect will be about the blood markers and how they may be useful for disease modifying therapies. All the aspects, how they may be useful, and also the challenges are coming. But in the latter part of the talk, I'll be talking about brain-derived Tau. And also we've got another marker, which is for peripheral Tau, but not just only for Alzheimer's. We're trying to link it to acute comparison between acute and chronic conditions so that we can move beyond Alzheimer's in this sense. Now, with the current drug approval, so I looked at the leaflet for lecanemab or Leqembi from the FDA, and there's one thing that they put, that confirmation of the presence of A-beta pathology prior to initiating treatment is required. Now, there were also, what I would imagine that they knew what they were doing, did not indicate how that should be done. So that opens up the field for us to think about what are the different ways that we could use to determine A-beta pathology in the brain. Of course, the classical ways is to do A-beta PET, which at present, these are how the trial aspects focus on. So this, we did this simulation based on data in ADNI. So these are real data when we measured phospho-tau 181 in the early days of phospho-tau. And what we found was that 20% of the population were about A-beta positive by PET. And so if, let's say you want to run a trial, so in this time, let's say not a trial, but let's think of it in the form of for drug. So let's say there are people who want to determine who is eligible for the new drugs that are being approved. How are we going to do it? Because the classical way is to go with PET. You do PET, and then you get to identify who is positive, and then you initiate. Because it also applies in this clinical trial aspect that we did. But the other way that can be done is by going with what we call a pre-screening approach. So with that pre-screening, then you would first go with blood tests, and that would enrich or identify who is likely to be eligible, and that before you initiate those treatments. Now, with this, which was based on clinical trial, what we found was that when you screen the same individuals, so this was based like a trial for, let's say you're looking for 1,000 individuals who are positive for A-beta PET. If you base on a population where 20% are A-beta PET positive, then in simple terms, you have to screen 5,000 people by PET. The cost is expensive, but even beyond the cost, how are we going to get the people and who are we going to target? We talk about inclusivity, we talk about diversity, we talk about all the aspects. Not many people are going to be willing and available to be able to go through all these scans. And also even the infrastructure is not there. We tend to think we have it, but if we can imagine, like if everyone is going and now with these drugs would require a PET, the infrastructure is going to collapse probably because we can't have everyone doing that. So if you base on PET, what we found was that by pre-screening with blood, 40% of that same population were positive for phospho-tau in plasma. So if we say, okay, that 40% now, enrich, you have that enriched population, which will bring it down to like 2,000 out of that 5,000. And we're thinking blood tests will come down to about $50. We're not there yet because the commercial one, those that are commercial now are pretty expensive. But hopefully we're going to get to this aspect quite very soon. And when we do this, you get to identify those who are positive for A-beta PET or A-beta in the brain. What we're really hoping for is that we will not end here. We actually will get to a point where the blood markers have been validated much against PET, and then would have identified cutoffs that are robust across instruments, across sites, so that we would not need to even do this validatory aspect. We just would base on blood test by itself, and that should work really well. So one of the examples that I would take is that there's this proposal of this like amyloid probability score from the Bateman lab at WashU and C2N. So what they did was that they have an algorithm that puts together the mass spec plasma A-beta 42 and 40 ratio data that they measure with the mass spec assay. And then they add ApoE genotype, and then they add age, and that put together, and they validated that against PET A-beta. So then they get to have what they call this probability score. So based on this density plot, you see like those who are likely negative for PET A-beta there's a high probability of those ones here. And of course, you get to see the other side where you see it this way. Now, the challenges that the field continues to see will be to how are we going to make sure that this is robust across sites, across measures, across cohorts. And that is, I don't think that is where we are yet. Is one aspect we have to continue to do, especially for assays from like Quanterix and all these platforms that are not built in for these aspects. So what I think we have to look at is, for example, take a lot of cohorts and maybe run a lot of them at the same time on the same reagents at the same center. Then we can identify and tease out cutoffs. But for those cutoffs to apply between centers, we need to have some of the blood samples that should be included, some quality control samples that will be included in these runs and will be available to all. And I think that's the way that we can start to really think about getting cutoffs that would apply across sites. Now, the other aspect that these blood markers could be useful for is to monitor treatment response. So there's an example here from recently when they did this donanemab treatment. So this is a paper published recently in JAMA Neurology. And what it saw was that for those who were on the drug, so this is phospho-tau-217 in blood, from baseline, those on placebo, you're not seeing changes, but those who were on the drug get to see continuous decreases in phospho-tau-217, which would mean that it's responding to amyloid. GFAP also showed a similar trajectory. This is NFL, and it wasn't really much different. Of course, it explains that A beta is really not an amyloid-related marker, and we've shown that multiple times. One aspect is also look at A beta 42, where you see an increase, because normally it will go down when the individual is at risk. So if you're going up, it means that there's less risk. This is really good to show that as a proof of concept, we can have responses to drugs that are measured in this way. But then there's also the other side of it, which we have been debating over the last 2 years in the lab to say, for example, what does phospho-tau measure? Is it an amyloid marker or is it a tau marker? So here we're seeing these changes here, beautiful. But if we were also initiating treatment against tau, would we see that change? So then is it like as a response of, is it a primary response of the amyloid changes or is that a secondary aspect? And these are things that we have to continue to factor in. Now, whilst we know that, okay, we can select for people who can go onto the drug, those who can to monitor the treatment response and also the changes, there are some other aspects, which would be like the adverse effects that are very much talked about. The area, the amyloid related effects, imaging abnormalities. So we don't have much data, so this is based on us teasing out to say, for example, with plasma brain-derived tau, which I'll come back to talk about quite a bit, we recently tried to tease it that would it be useful in this context. So we looked at this cohort, for example, where we saw that for stroke mimics, you have low levels, those with a transient stroke, you see like that, and those with manifest stroke, the levels tend to be higher. Of course, the numbers are not the largest to look at that. But what we also see in a different cohort was that, so those with subcortical stroke, the levels were low, compared with those who actually have like a cortical manifestation of stroke. And that when you base on the correlations, you get to see that BD tau was actually represent quite a real good correlation for those that have the cortical, with the cortical diameter, the stroke diameter in the cortex. So with this, could it be useful to try this marker, for example, to say, would it be able to report on these changes that we see for drug responses? We don't know yet. We're trying to get access to some of these trial samples to be able to measure, to show if this would work. Another example is from acute ischemic stroke, where what we saw was that if you look at BD tau, for those who have good outcome and bad outcome clinically over time, so these are the time points, so upon admission, and then immediately after therapy, and 24 hours after therapy and 72 hours, those with bad outcome kept going up. So when you plot it this way, those with bad outcome actually kept increasing. And this, we talk to the stroke people, and what they tell us that this is expected because the neurodegenerative effects will continue to manifest over time. And of course, it shows more in those with bad outcome compared to those with stroke outcome. And then if you look at predicting 3-month functional outcome, also kind of something similar. So then would it be that plasma BD tau would be useful in this context to be able to track what is changing in terms of stroke-related abnormalities that may be of use also to when it comes to when it comes to drug effects. Another aspect, which I think we've talked about the drugs, but it's going to cost money. And also we're going to have a lot of people who would be maybe eligible. We might get to a point where we have to prioritize who should get the drugs and when and how fast. So what we sought to do there was to say, for example, if plasma BD-tau is a neurodegeneration marker tracking neurodegenerative changes in Alzheimer's, then it should be able to track according to amyloid and neurodegeneration positivity. So what we did here, so we took the same data set, we look at BD-tau against CSF total tau because it should be a surrogate of total tau in CSF. We did the same thing for plasma total tau currently. And also this is NFL, so sorry, this should be plasma NFL. Now, what was interesting was that for those who were amyloid positive and neurodegeneration positive, so A+, N+ per CSF, for the same individuals for BD-tau, we saw these two clusters. And then for the same individuals, for we look at total tau and look at NFL, you did not see them in that clustering. So we're like, what would happen? What is happening here? So let's dig deeper to look at that. And then when we tried to look at that, what we found was that if you base on Gaussian mixture models, based on the populations, you get to see like, a clear bimodal distribution. So you get to have a cutoff. Now, what we did find that within this population that are amyloid and neurodegeneration positive, those who have higher levels of BD-tau actually tended to decline much faster, somewhat like a rapid cognitive decline is over the next 8 years, kept going much faster, compared with those who had lower levels, who also declined, but at a slower rate. And this is based on CIRAD and based on TMTB. So then get to argue that probably this could provide ways that we could get to prioritize who should or who needs access to these drugs in a quicker fashion, in a more timely manner, right? Now, I'll go back to talk about this aspect where we say the phospho-tau measures that we have, are they actually tau or are they amyloid markers? And this is something we've been talking about for like 2 years. We don't have a resolution to it. So there's a cohort from this triad cohort in Montreal, where, so we did say, okay, let's don't use plasma, let's use CSF. That should be much simpler, right? Now, when you take CSF and you take the same individuals, are paired individuals that have amyloid PET and tau PET measures, and then look at these phospho-tau measures, what we get to see was that the associations with amyloid PET for each of them is stronger compared to tau PET. So would it then be that, phospho-tau is tracking amyloid, which sounds quite counterintuitive because you have a tau marker tracking amyloid, whilst in CSF, for example, we don't see that. If you based on imaging also, they seem to be quite, separated apart. So we're interested to see more. So these are the scatter plots basically telling the same thing. So what we did was to say, okay, let's go back to some biochemistry that I really like, and then let's do some digging. So we went to take brain tissue, extract, and then extracted it into different fractions. So we get a soluble fraction, we get the insoluble, like different densities. And those that are most soluble should be the ones that should be similar to what we see in CSF and blood. So here, what we did was to look at phospho-tau 217, for example. Now, in that soluble extract of the brain, that should be similar to what we see in CSF and plasma. Phospho-tau 217 was correlating really well with A-beta 42, also with A-beta 40, and then you have, of course, you have this inverse relationship. Now, we have used a different method to measure tau aggregates, which we're working on a paper to show that it's quite similar, like it has good association with tau PET, for example, but this is in the soluble pool. So we're not talking about the tangles, but we're talking about the most soluble, the smallest soluble form that people could say oligomers, for example. When you take phospho-tau 217 in this same population, the association with that is not there. So then arguing that it's more reflecting the amyloid changes and not the tau changes. And that supports the data that I just showed in using PET. Now, if this is the case, what about the other markers? For example, the other phospho-tau markers. So we went on further. This is the FRET assay I'm talking about. So this is based on energy transfer, that it can only bind to a single epitope on the protein molecule. So the signal is proportional to how many molecules are there. So the more the aggregates or the larger the aggregates, the larger the binding. Again, we see like, for example, 231 showed no association with it. 217, 181 was sort of in between. And that also makes sense because we've shown that 181 is more like, more clinical, a clinical marker, like when people are in the symptomatic stages. And interestingly, phospho-tau 397, which is more C-terminus, seem to have a really perfect correlation here. So more telling us that it looks like this is what you get when you have changes that are being reflected. These are more like tau aggregate markers, and these are more related to the amyloid. What we are doing is to provide more mechanistic understanding as to why this is the case in upcoming stories that we are showing. And this is so that this would argue that, for example, if you have soluble aggregates, the association between the soluble aggregates of tau in the brain and then phosphorylation is not the same. So some pick out earlier where you don't have any tau there, for example, and then it goes like that. So in a nutshell, what can we say about in terms of using this as standalone markers, using phospho-tau or all these blood markers as standalone markers of brain A-beta pathology for drugs? What we can see is that, for example, can we use plasma A-beta? I talked about A-beta, phospho-tau. If we're using phospho-tau, which form of phospho-tau should we use? And from which company or which lab or what? GFAP also has been shown a lot to be a surrogate for amyloid changes or brain-derived Tau. We actually think brain-derived Tau will be more of a telling about the extent of neurodegeneration in amyloid-positive individuals in the context of AD. But then we don't have cutoffs. So these are some of the challenges. We don't have cutoffs. Batch-to-batch variation is actually real, and I'm sure Cindy and people tell you what we see all the time. But then there's even less in CSF because the CSF assays now, those that are FDA approved, they've been able to correct for batch-to-batch. You see tiny ones, but not as much. But the blood ones, we have to do much better in terms of source. Now, it's all well and good if we see a blood or access to therapies, and then we have to prove people have amyloid in their brain. But it's not everywhere where we're going to have PET scans. And that leads to how are we going to validate these ones against, because if you have places where you don't have PET scans, how are you going to work out with validating the blood markers against the PETs to be able to say, okay, now if you base on these values for the blood markers, you can use them to show someone has amyloidosis or not. If we also base on CSF and PET, they both reflect and they both agree really well, but for some individuals, so maybe about 10%, you get to have a discordance. And this is important because it means that for 10% of individuals, depending on which one you're using, you might be excluding them or you might be telling them what may not actually be the case. Last but not the least, we have to look at demographics and lifestyle factors that can affect these aspects. So I'll talk about like some of the comorbidities and some of the ways that we can try to address them. First, I'll talk about sleep. And this is quite serious that we feel like, okay, we should sleep better, right? And then we all should sleep, but we don't sleep. So this is a study, a sleep study that has been done at Pittsburgh Sleep Center. They've done it for ages. So we spoke recently and then they pulled the samples for us. Now they did a 3-day intervention, or no intervention is an observation, but they had the individuals, actigraphy measured and all. And then day 1, they came in, they took all these measures, took blood, and then they were sleep deprived. So between that day 1 and day 2, they went through sleep deprivation. And then between day 2 and day 3, they were allowed to recover. Now, this is A-beta 42-40 ratio. It's all over the place. They're still doing a more extensive analysis to tell us what is happening, but it looks like those who are here are really the ones who are declining faster. But just to remind ourselves, for A-beta, the less, the worse. So it would mean that theoretically, those who are down here are those who already have amyloidosis in their brain. They go down during sleep deprivation, but the effect is less compared to the apparently healthy individuals who sit up here, who go like a free fall, right? And then depending on how far you came from day 1 to day 2, it also tells how quickly you can rise. Because those who come much faster, they don't rise. Like they're not able to compensate for these effects. There's data showing this based on PET imaging, but we haven't seen that with blood. And it looks like what is being shown by PET also is reflecting in blood, and that means we should sleep much better. But also, so we looked at phospho-tau. For example, phospho-tau 181 was very squeaky clean. It looks like there's no change across board, right? And then when you look at NFL, also no change. You look at GFAP, there's no change. So in a sense, what my argument to be that if sleep deprivation is affecting A beta without affecting other markers that are linked to Alzheimer's, then the changes that are happening are independent of Alzheimer's, because A beta would lead to effect that should reflect to tau, it will reflect to GFAP. If they're not, they may be linking to amyloidogenic, the amyloid peptide processing, but not Alzheimer's. This is something that we need to prove. I also point to the question that what if we're only using A beta as a measure for let's say A beta in serum or A beta in plasma as a measure for brain amyloidosis. If that is the case, if you measure someone who has gone through sleep deprivation, that can affect their levels and that can lead to false positives, right? So these are things that we have to factor in. Of course, we've seen this figure a lot of times with comorbidities, with this Michelle Mielke's paper, looking at from the Mayo Clinic study of aging, looking at Z-scores, so looking at associations of all these factors with these plasma markers. And then we look at those like kidney disease, for example, chronic kidney disease, then the effect size was as strong as those with amyloid positive. So that would argue that if people have kidney disease, it can affect their amyloid positivity based on these plasma markers. When I saw this paper, I was like, yes. Not that I was happy, but was like, this is something I was really saying in the early days that we are not there yet. We need to do better. We need to do more, because it's more of a sink system. If you have, a faulty sink in your kitchen, in America is faucet, right? System in your kitchen, and then you keep pouring water, and then there's not going out, then you have more retaining. So those that are being retained, all the junk will still be there. So if you take a scoop of water compared to one with a clean, sink, then the quality will be different. And this is what we are seeing here. It just tells us it's biology doing its work, and that we have to also do better to try and address this. So we looked at a cohort recently we haven't published, but so like in phosphatide 181, for example, if you look at the cohort, and this was not those with kidney disease. So those with so just the impaired function. So they are not those who have a diagnosis of kidney disease, but those with just with their EGFR just going beyond the normal range. And what you get is that in the individuals with the impaired, you have the AUCs go down. So the accuracy of the marker goes down, both in the entire cohort, or if you just focus on the cognitive only impaired. So it means we have to do better. And to us, to me, what is exciting part is like going after a challenge with science to say, okay, how can we try to fix this? How can we address it in a way? And then so what we try to do, and this is actually one of the things that led us to BD Tau, was to say, okay, if we look at Tau, for example, in the blood, there are different sources. Now we are always excited and interested in what is coming from the brain, but it's just a tiny part of what we see in the blood. Of course, when you get a tube of blood, unfortunately, you can't differentiate which protein is coming from where. It's just the full picture or the complete picture. But then they could come from different sources. And these are some of the key peripheral sources of Tau based on the expression patterns. Now, what we thought was, okay, in different conditions, you get to see, for example, brain-derived Tau might increase and peripheral Tau doesn't increase. An example should be Alzheimer's disease, right? Where we think the changes are coming from the brain and not from the periphery. Now, you can also get other potential scenarios where peripheral changes go up, probably people with kidney disease, changes will go up in the periphery, but not in the brain. Or if those individuals are presenting, let's say, comorbidities, then you will see both. Now, unfortunately, currently, the marker we have for these Tau form, total Tau, it just reflects the predominant fraction. It doesn't tell you where it's coming from. So it just switches based on the flow. And I'll come back to show that much more carefully. So we looked at one cohort, which is this mesamine cohort based out in Wake Forest. And then what we saw was that if you look at brain-derived Tau or NFL and NFL, you get to see the EGFR associations for brain-derived Tau. It's not there. But then if you see NFL, you have a strong association with EGFR. And actually, we went back to do, because this was a cohort, so good to point out, this is a cohort. This was a cohort with huge levels of cerebrovascular disease. So they are not the classical cohort we see every day in our research ones. It means that you need the people with a lot of the mixed diseases. And it was quite interesting that we didn't see that. So we went on to look at a Norwegian cohort and a very wide cohort, a very healthy cohort. And then we saw about the same thing. Of course, the effect was less, but even when the effect is less, you see that you still be able to abrogate the effect. And then the age aspects were also taken away, where you see with NFL. So here, for example, this is what we saw. For plasma BD tau against age, you don't see that from 40 years across to 80 years. Total tau basically is just like that. So basically telling us that what BD tau is doing is basically providing us with a better and improved total tau assay. And then, but NFL has a strong age effect that we have seen over and over. So telling us that potentially these effects of comorbidities where kidney disease, or for example, an other aspect that can lead to tau building up in the blood, and that can affect the results that we get for these markers. Probably BD tau could help to address that. We're trying to look at, if you take ratios, for example, phospho-tau to BD tau, would that be a better reflection of taking away these effects? So in concluding this part, blood markers, we think blood markers are key roles in amyloid therapies, and that for all these aspects, for eligibility screening, how to monitor the therapy, and also potentially adverse effects. And that p-tau seems to be reflecting A beta and not more of tau pathology. We new markers that really reflect tau pathology. And this is something that we have some pretty nice story on coming up, and some of the challenges that we need to look at. So I'll go to the second part to say peripheral tau and brain tau, or brain-derived tau, looking at the in different conditions. So we've talked very Alzheimer focused. Now we're going to expand to look at different conditions, for example. So here, I'll go back to this, that is a matter of the sources really telling you what you get. And that with these three different scenarios play out more often when you're looking at the sources of tau. So what we did was that recently we talked about this. We developed an antibody that binds at this junction. So for tau protein, there are different isoforms. There are about 6 isoforms in the brain that predominantly expressed in the brain. This is the longest form of it. And that between the different exons, between exon 4 and 5, you have to have this contiguity. So like a very continuous sequence here. But then when you have a big, what they call big tau, because it's basically almost double the size of the longest form of the 6 isoforms that are more in the brain. Peripheral tau is mostly in the peripheral organs. Of course, it's been shown that they also express in the brain at much lower levels, and also expressed by neurons that project out of the brain into the periphery. So even if it looks at for some neurons, you could even see this expression in some parts, but not others, just in those that are projecting to the periphery. So then we got an antibody that binds at this junction. So that antibody will not bind when this junction is broken and you have this inset that has come in. Now, what we've also done has been to develop another antibody that binds just at this inset. So by that doing, you can differentiate between potentially brain-derived sources of tau and peripheral sources of tau. In one of the early days, like for the brain-derived tau, we looked at this validation. This was the antibody against an antibody for tau exon 4, where it shows basically showing that when you have a contiguous sequence, so when that contiguity here is not broken, the brain-derived tau antibody binds, and also the exon 4 antibody binds, because exon 4 is there. But then when you have just the exon 4, and then you break it, you have this insert here, so you have the 4A insert, brain-derived tau will not bind, but the exon 4 will continue to bind because the exon 4 antibody site is there. And when you have this broken and you're just looking at this site and that site, both will not bind because you've taken away these 2 areas. And again, when you have that broken and you have looking at all these 3, the exon 4 antibody will bind, but the brain-derived tau will not bind because the 4 and 5 junction is broken. These are ways that we did the validation. We've even gone ahead recently to provide more validation in this sense. For example, using mass spec, so we look at immunoprecipitation and mass spectrometry. So we took CSF samples, we conjugated the antibodies onto beads, and then mixed with the sample, incubated for some time, and then we'll pellet out, take out the beads, and then purify and then run it with mass spec. Now, what we see here, if we use a tau J antibody, it picks out fragments that correspond to only the CNS tau. So this is the CNS tau, including those that cut around this junction that I just talked to you about. It doesn't pick out elsewhere. Now, when you use a positive control and HT7, which binds at the region that is common to all tau isoforms, regardless of where they're coming from, it also does the same thing, or it picks isoforms that correspond that way. But then if we use a new, the new antibody that we have talked about for the peripheral tau, And then we run it against the recombinant form that goes over the peripheral region. It picks out really long fragments that go into this exon, and then even an extra exon that correspond to big tau. So in a way, showing that these antibodies do what they're supposed to do, binding to the brain-derived and peripheral sources of tau. Now, this is, to me, the fun part. So we look at, say, let's get the dynamics. Now, if someone has Alzheimer's disease dementia, which is like in a very advanced stage, which has got the AT and N positivity, what happens to the dynamics? We see that peripheral tau does not change much. Total tau does not change much, but BD tau changes quite more. Now, we look at here is about fold change of about 8. So it's not the biggest. So it would mean that whilst this is speaking out the changes that happen in blood, total tau is not reflecting that, because the change, the pool of blood, the pool of peripheral tau in the blood is much more that total tau does not decipher that two changes. I'm quite interested in what I call the high flyers here. Who are they? Do they have concomitant disease? And this would be the perfect way to look at those that might have, let's say, kidney disease or diabetes and Alzheimer's. And then that would be a way to prove that, like, if you can use this one to pick out changes that cut across. So this is an example of a scenario where you have BD tau changing, but peripheral tau doesn't change much, and as a result, total tau doesn't change. Now, when we switch to look at neuro-COVID, of course, the pandemic was not too kind to us. Then BD tau changes a massive full change of 50. Average of 50. Now, because the effect is so massive, it means the amount of tau coming from the brain is so overwhelming, then total tau is basically a mirror image of what you're seeing with BD tau. Again, peripheral tau doesn't change. So that would tell us that in the onslaught of neuro-COVID, the changes that are being seen are truly coming from the brain, and that they are not peripherally derived. Now, when we look at TBI, so there's a polytrauma cohort, but most of the people have TBI. What we see is that compared to healthy controls who are in green here, and then the individuals who were followed for 10 days, those with and without shock. Now, those with shock had higher levels, but then over time, they were declining, all of them, both whether they had shock or without shock, so sort of projected it this way. But by 10 days, that's why the levels haven't come down. They haven't really come down to the levels that you have in the healthy controls. So they still have some time to go to catch up with it, to actually recover. Now, if we use peripheral tau, it's just squeaky clean, no change. So it means the effects are also coming from the brain. And then when we use total tau, it somehow tells us what we're seeing with BD tau, except that by day 5, everything has normalized to the levels of healthy controls. Whilst if you use BD tau, it's telling you that the effect is actually much more. So for example, if we base on one individual here, and then if we base on total tau to say, clinically, you're good to go after 5 days, in reality, that individual may not be, because they truly have not, the effects have not cleared out. We get these questions of, okay, phosphotaus are really specific for Alzheimer's. Then for me, what I say is that it has to be context dependent, because physiology is really complicated. So it's difficult to have a marker that comes out only when you have like one specific condition. So we look at the same individuals over time up to like 10 days. But then if you compare to controls and Alzheimer's disease, like ATN people, by day 10, BD tau has come down. That's when it comes down to the levels of those with Alzheimer's disease. So all these massive changes are like, folds higher than what you should see in Alzheimer's. Similar for total tau, except that by 10 days, by 5 days, it's come down. We see similar for phospho-tau 231 also, and also for phospho-tau 217, which means that when you have, for individuals have these, traumatic events that happen to the brain, they get to be markers that are affected. It feels like, like a tsunami, like an earthquake, a hit, and everything comes down from the brain to the blood in a short period of time, independent of what they are or what they represent. This was based on TBI, so like in a mixed population. So we looked at severe cases of TBI. Now in severe TBI, what we see is that similarly also monitored for up to 300, so over 1 year, to compare to controls. By day 7, BD tau had cleared about 50%. So the rest of the signal stayed, and it had to be cleared over the next year. Total tau in that same set of individuals was telling us by day 7 that 90% of the signal had gone away. So it was overestimating truly the changes that had happened. NFL, as we know, had a different trajectory. So NFL takes longer to really show up in blood. And that by day 7 was when it had peaked. Of course, by 1 year later, it had come down. Similarly, phospho-tau, here we looked at 231 showing the same trajectory. The reason we did 231 was because our TBI has been linked to say like this cis version of phospho-tau 231. And clinical aspects, what we saw was that for the BD-tau levels, when you based on those who were clinically classified as poor outcome, the levels were higher compared with those with good outcome. But then, the changes were still happening in both, and that statistical difference is separate between this. But I really don't see this as anything much. By basically telling us that those who have poor outcome in the clinic and those who are good outcome at day 0, you could use BD-tau to track what is changing and what is going on. So, in conclusion of the second part, we get to see that the interplay of brain and peripheral tau, when looking at the dynamics, it starts to provide us quite a nice picture as to what might be happening to conditions that affect the brain, and then that levels reflect in blood. And that it looks like in Alzheimer's disease, in neuro-COVID, in TBI, the tau changes we see look like they're coming from the brain, because we don't see those when we use our peripheral tau marker. And the levels of the rate of normalization does vary between total tau, phospho-tau, and brain-derived tau. And with all that put together, we can say that in these acute conditions, for example, BD-tau would be providing a use in terms of telling us clinically, predicting recovery or predicting outcome. Of course, these individuals would be amyloid negative, so that decouples its use in Alzheimer's disease, where the individuals would be amyloid positive. But it looks like the neurodegenerative aspect can be quite useful for tracking outcome in these different conditions. And on that, I end here. Thank all the people who have been very contributing to this massive amount of work. Thank you.
Great, thank you for a wonderful overview. 2 questions. One, as a non-Alzheimer's person, how well does brain pathology correlate with functional outcomes?
That is one thing. So we're actually doing that now in one cohort I quite like, where I was more like a natural history cohort. So those quite similar to what you have with RAP here or AFA, following people who were cognitively normal and then over time. Now, what we do see, so that's like it has 8 years of longitudinal data. It was a population-based cohort, so not very selective. What we do see is that it does vary. So when we look at all the different cognitive domains, some of the executive, some of the functional aspects, what we do see is that these markers associate differently with different outcomes. Now, but one thing that stands out is memory, that all of them associate quite well with memory. And that makes sense that we often use memory as the first changes that happen in these cognitive aspects. But when you look at attention, when you look at executive function, when you look at all these other ones, some you have like NFL predicting the change, some you have phospho-tau predicting the change, some is A beta, so they're not really coordinated out there. But at least we can agree on memory.
That's fantastic, Tommy. Thank you. There's an online question, and I'm going to ask it because there's a part 2 that's my question. So related to those tau markers, the plasma tau markers, the 217, 181, et cetera. Pete online asks if you can monitor for rate of accumulation over time with patients who are progressing from normal status to Alzheimer's disease. And then my second question is, do we need to choose the tau isoform based on where we think the person is? Because the data you showed that one works better during the preclinical phase versus when the person has the disease. So that's a 2-parter question for you.
Yeah. So the first part is, can these markers track the rate of accumulation, right? Which and would that be for A beta or for tau? Let's say for A beta. I would think yes. So we haven't done that quite well, because you can imagine with the A beta changes, you get to have like because we often use A beta as a readout. So, but given some of the early data set that we showed for like 231, it might be useful there. I think 217 performs just as good in that context. And then tracking to see when the amount of A beta peaks are in the brain. What we think might be useful there will be to say, at what point do these amounts level out? Because I think like similar to what we see with A beta PET, where at some point, you have a lot of levels that you don't see much more happening. You might see the same thing with these markers. And it correlates with data. And that's one thing that I find quite fascinating, because oftentimes, like where we can't understand things, my pastime is to go back and read the old papers. Some like papers in the 90s, the 80s and 70s have a lot of information that we're chasing after again. And what they show is that by neuropathology case series following, that they see like, it looks like when you see like that time, 217, they did not look at it because it wasn't a big deal then. They had 231, it picked out very early changes, and that's it. They didn't see it again. And then they picked the others in the middle. So more like 181 was like it's sitting in the middle, where disease was just about in the middle stage. So based on from where you go from intra pre-tangle to intracellular tangles, and then the extracellular and the ghost tangles, where 396 also comes in. So it matches this data I just showed, that these markers associate differently with tau, but at the same time, the reverse, it's what they have with A beta, if we think the A beta changes happen before tau. So it gives us like a two-part picture, which becomes quite useful, depending on which one that we want to do, choose for. Whether we want to go for A beta or we're going to go for tau. In terms of which one that we should choose, I don't know. Well, yeah, but then I don't think brain-derived tau, I think like what might be useful is that at least that phospho-tau is going to be useful in picking out who is picking out amyloid positivity. So that will be what we need, that, and then maybe brain-derived tau comes in to tell who is going to decline fast or who has this extent of neurodegeneration that p-tau may not be able to pick out that much. And I think that combination would be useful, and maybe taking a ratio of them will give you, two things in one.
So basically a panel of tau markers.
I think so, and it's quite funny that now it looks like everything is coming to tau mostly, where we suggest like tau is more A, T, and N by itself, which biologically doesn't really make sense. But the more we probe, it seems that's where it's still going. So then, like the functional aspect or the mechanistic aspect is what is missing, that we're hoping to fill the gaps in soon. But it looks like different regions of the tau protein respond to different aspects of the pathological insults that happen in Alzheimer's. And it would be quite nice if we're able to stage them that way.
A question here. Excellent talk. Just was wondering if there is any link between an association between kidney disease and the development of cognitive decline and Alzheimer's disease. Just thinking on those reports that show that A beta can actually be internalized into the brain from the periphery.
Yeah, so in terms of, as we often say, like, almost a lot of things are associated with or predict Alzheimer's, but then it also might be in the sense of, because in the populations that have Alzheimer's, they also have a lot of other conditions. So it may not be one being a predictor, but then because they have a whole package of these aspects. I would think for kidney disease and from like A beta from the periphery going to the brain, maybe from a mechanistic point, because nothing is impossible, but it looks like maybe quite, I would say, less plausible. What I think might be the link there will be what I showed recently. Like if we're using only blood markers that can be affected by both, and I think this is where this is coming from. When you're using hypersensitive assays, which is nice because you're amplifying the signals that you want. At the same time, you get to amplify the signals you don't want. So if you're looking at things in blood, you want to amplify things coming from the brain or things from the periphery that are also there. Based on the abundance, you also get to amplify them. And that is how they can affect it. But what would I think would makes us quite good as scientists, like for all of us, is that We anticipate a problem, we see it, and then we get back to work to say, okay, how can we try and fix it? Yes, Andrew?
I mean, what an outstanding presentation. The work is great. Sorry about that. So thank you for your outstanding presentation, and we know your work is world-renowned. So a very basic question, I mean, many of us are clinicians here and we see patients with dementia. Do you think a day will come when a patient is referred to the clinic and all the physician has to do is collect the blood, measure plasma P217 and say you got Alzheimer's? Or you think that it'll be a combination of these tests plus still the physical exam and MRI scan and everything else we do to diagnose dementia? That's number one. And number two, is much known about the effects of race and ethnicity on all these biomarkers in an area you and I know a lot of deficiency, but are there plans to, at a larger scale, study those effects? Thank you.
So on the first one, I can imagine if you asked us 2 years ago, no one would, or 5 years ago, no one would dare think about that. But I think, yes, I think genuinely, I think we're getting there because, you know, there's been a lot of validation studies showing that in different cohort, different contexts, these markers associate with the brain changes and then can predict them. So I think we have a lot of data, dozens published. So what next do we do? Is to use them. I think the only part that we have missing is one, to have assays that clinically are robust from day to day, because we don't want to, currently what we do, like the platforms we have are more research-based. We put a lot of samples together, we measure them at once, and then we measure the next day. If you buy from commercial sources that are based on whose platform is based on these laws, they don't care about the batch to batch variation. But if we switch to, or if we're able to develop assays that address these batch to batch variations, then that will be fixed. I know I can't mention names of companies, but some of them that are already in the clinic, like clinically approved labs, these platforms, they try to adjust for batch to batch changes. So these will not be fixed. It will not be very evident in those ones if we're using them. And they are also done in a way that you can send one blood sample from a single patient to the lab, and they can measure that and get the result. They don't have to wait to get a whole batch to run. That is one aspect. One aspect that I think there that we still are failing is that we think of it in the large clinical scenarios, like, you know, UW Health, we can do that. But if you think of people, let's say who are going to practices in small towns and villages, what's going to happen? They will take the blood test, but if they have to send them to Madison to be done, it means they have to send the patient to come here for the blood to be collected, because we want the blood to be collected, processed at the same time and fixed, right? We don't have that gap. So that's another problem that we're looking at. What we have, data we have on that, has been we're trying to sample different blood collection tubes to find those that have protease inhibitors. And it looks like we found one that does the job. So you can collect blood into that tube, leave it at room temperature for like 24 hours. And we actually done time course. And then the most notorious marker is A beta, but it looks like it fixes it, that you can maintain the levels quite well. And this is what we're thinking that probably we can think of like doing like on a large scale validation to say, does it work? And does it work on different platforms for different measures? So that we can think about saying these tests are going to be available for all, right, in that sense. For race and ethnicity, I try not to go there this time because I just say it's complicated. Because we all agree that in memory clinic cohorts, like many of the cohorts we have, they don't have a good combination of people from different backgrounds. And even that, for people from, like, for example, if we say non-Hispanic whites, there are people who are at the bottom of the ladder, those who do like, you know, more menial jobs, who would eat less healthy, because healthy living is expensive, healthy eating is expensive, who have more combination of diseases. They are less likely to come in for the research data that we have. So we have these data, they're great, but they're shiny. And they may not work well for everyone. And that's what we should do, is to bring in this aspect. So with that, at least, like, if you ask me, what we are trying to do is to do quite an ambitious project that we think AFM would join, to say that we're taking like about 2,000 cohorts from the whole world, including all 6 live continents. And then where we have the cohorts have different different populations, so different racial groups, different ethnicities, but to say within each identification, self-identification, what do you see? If you compare the top of the ladder against the bottom of the ladder, what do you see? Because what I think will show is that the health disparities will be the biggest predictor and not the racial differences, because then oftentimes we have good people with good quality of life here. We have those from the other side, but with poor quality of life. What we are looking at is the health disparities. They are not the race or the ethnicity. Of course, the ancestry have effects, and this will allow us to be able to tease out and apart. Is it the health disparities? Is it the health outcomes? And then how well do we also bring in ancestry, for example, and lifestyle?
Fantastic. So in other words, race is a marker for disparities in life exposure. So yes, okay. You're singing my song. Okay, so Rob Stryker wants to know if older HIV, persons with HIV also show changes in Tau in their brain?
And send the results, but we haven't had it back. So everything we do is blinded.
Tuned.
Yeah, and then we send the results, and then the people will decode and do the analysis. So yeah, so hopefully we'll find out soon.
Hey, Tommy. Oh, that was loud. Hi. That was an excellent talk. Just, more of a meta question here. So I still remember the first papers from your group in Gothenburg with Henrik and Kai about 20-something plus years back, that defined, the 3 key markers for Alzheimer's: total tau, phospho-tau, A-beta, and indicated the pathologies that these 3 markers tag onto. And then fast forward again, 20 years forward now, as you just mentioned, it's like everyone now is saying that phospho-tau is A, is T, it's N. How did we get to that point? Like, was there a watershed moment, or it was just kind of a kind of drip that occurred to get to this point where now we're saying that phospho-tau tags amyloid and tau and everything else?
Yeah, I don't know. So I joined the field as my background wasn't more in this area, but I've loved going back and reading some of the papers. Like I always embarrassed Kai with the first paper on this, the tau markers, where it showed phospho-tau and total tau. And he told me the story about the publication because he sent it to a big journal, and then it took years and months, and they rejected it, and then he knew that it was something going on. Now, what I think has happened, I think it comes from improved understanding of the biochemistry, of the molecular biology, which to me, that's what I love. Like, let's look at the bits and pieces. And that's one thing I have really loved. Like, you can really be playing, like, okay, get crazy idea. Let's see, can it work? And then if it works, you get see it going, being translated, and then you could see it being tested on actual real humans, and you look at, oh, you can make sense of what is going on. That's what's happened. So I think over some time, we got those markers. The CSF were happy. They went on for a long time, validated. We had imaging also joining in. But what we agreed at that time was that, oh, you can't use those in blood. And blood was like really difficult. And eventually, so for example, for me, what brought me into this area, like when I started working on phospho-tau, because I decided to work on phospho-tau for blood because I heard at a conference, some people were saying, well, phospho-tau, you can never get it in blood. And I said, why? But they said, well, it's so difficult. Like people have tried, it never worked. And that was my kick to say, okay, let's try it. But what I did find was that we were basically following the choir. We're using the CSF assays and testing them in blood, and we're saying it doesn't work. It was not that it did not work, it was that we're looking at what we're trying to do, just paste the picture. What we should have done was go back and try to do a more holistic understanding, mechanistic, what is going on, the biochemistry of tau. So what we found, the tau was more N-terminal to mid-region in blood. So you have more truncations coming in, and that's where most of the signal was in blood. And that was the breakthrough for us with developing tau markers in blood.
Okay, so we have many questions online that we're not going to get time for. So I think with that, I'll just say thank you for a fantastic talk, Dr. Karikari, and hopefully more to come in your discussions today. So thank you.
Thank you. Thank you for your patience.